Okay, in this video I want to talk about two topics. I want to talk about the idea of total internal reflection, and I also want to talk about dispersion. So that's going to be sections 23.8 and 23.9 in your text. When light travels, from a more dense, that means a larger index of refraction, to a less optically dense, that's going to be a lower index of refraction. So when it travels from a higher index of refraction to a lower index of refraction, it refracts away from the normal. Let's look at what that might look like. So here is our two materials. We know that this index of refraction is greater than this index of refraction. Here's my normal. In comes a beam of light, and it refracts away from the normal because it's moving into something less dense. Here comes another beam of light. It too refracts further away from the normal. If I make that angle even larger, its angle of refraction at some point would work out to be 90 degrees. This is called the critical angle. Anytime light is incident at an angle greater than the critical angle, you get total internal reflection. The light cannot escape because the angle of refraction would be more than 90 degrees. Okay? Mathematically, this is really pretty simple. NA sine theta critical. So we're starting in this dense, high index of refraction material. The critical angle, theta critical, occurs when NB equals sine 90. When this would equal sine of 90. Of course, we know sine of 90 is 1 all of the time. So I end up getting NA sine theta critical equals NB, which means sine theta critical is NB over NA. Notice that will always be a number less than 1 because we said the original medium has a greater index of refraction than the second one. So our critical angle is simply the sine inverse of the NB over NA. Honestly, I don't really even ever remember this formula. I usually go back to critical angle happens when the refracted angle equals 90. And I just set it up and I solve it just like I would do any refraction problem to find the critical angle. If you prefer this, you can certainly use this. It works perfectly fine. Let's suppose we work an example. Let's see. suppose we have light in glass, which has an index of refraction 1.52, and it's moving into air, which of course has an index of refraction of 1.00. And we want to find this critical angle. Doesn't matter how we draw it. I'm going to put the glass here and air here. There's my normal or my perpendicular that I have to measure from. And what I'm saying is for what angle, that angle is called theta critical, would refraction hit 90 degrees. Any beam of light that's coming in at a larger angle will be totally internally reflected and it won't be able to escape. So let's go through our math here. We've got glass, that's our initial. So 1.52 sine theta critical equals 1.00 sine of 90. Well, all of that will just equal 1. So sine theta critical will equal 1 over 1.52. I just have to do a sine inverse. And I get that the critical angle is 41.1 degrees. So right about 41 degrees. What that means is anytime this angle is 41 degrees or more, none of the light will escape. Okay? Generally speaking, the higher the index of refraction, the smaller the critical angle. If instead of a flint glass, this had been a diamond, well, that would have been 2.42. If I had divided by 2.42, this would have been a much smaller number. This angle would have come out to be around 24 degrees instead of 41 degrees. The high index of refraction of a diamond is what makes it so sparkly. Two things are going on. One, light travels slower through a diamond because it has a high index, so it literally takes a little longer to travel through. But second of all, diamonds are cut in such a way that it's hard for the light to escape once it enters because of this total internal reflection. So the light tends to bounce around in there a few times before it can get out of the diamond. So it makes diamonds and other types of gemstones that are cut well to look sparkly. Okay, so let's look at an application here. Theta critical is 41.1 degrees. Let's suppose that I have a 45, 45, 90 prism. So I can draw where it looks 45, 45, 90. There's my 90 degree angle. And these are both 45 degrees. It's a pretty typical kind of prism. And I take a laser and I shine the laser directly at the prism. Well, if this is 90 degrees, 100% of that beam will most likely enter right here. But you'll notice that when I draw the normal here, that's 45 degrees. Well, the critical angle for this glass prism is 41 degrees. Anytime the angle of incidence is greater than 41 degrees, you get total internal reflection. Remember, this is incident at 0 degrees. Perpendicular is 0 degrees, so that went through no problem. But here we're at 45 degrees. That means all the light will be reflected, and it will be reflected at 45 degrees. When it hits here, well, that's also 45 degrees from the normal. So again, we get 100% of reflection or total internal reflection. It will also reflect at 45 degrees, but when it hits this, it will be perpendicular. If we were actually in a lab, and perhaps we'll find a simulation for one of our labs where you can play around and see this, we could easily illustrate that property with one of our little lasers and a 45, 45, 90 prism. Okay. One of the bigger uses, I've said, fun thing is it makes diamonds look sparkly, but a more practical use is fiber optics. Fiber optic cables are made to be thin and flexible like this. But because they're made of a material with a high index of refraction compared to air, if you have a light signal that goes into a fiber optic cable, it tends to bounce off and the light will simply travel through the cable like this with very, very little signal loss. Fiber optic cables are used in all kinds of information sharing. I think we have big bundles of fiber optic cables even through the oceans or under the oceans. Okay, so fiber optics are pretty much, I want to say, top of the line for transferring digital information. Okay, and it's because we can shine a signal through light, whatever that signal might be, and it will stay in that fiber optic cable because of total internal reflection. Okay, the other idea that I want to talk about in this video is the idea of dispersion. The speed of light in a vacuum is the same for all wavelengths. We know that light travels at 3.00 times 10 to the 8th meters per second in a vacuum. And it doesn't matter whether we're talking about a radio wave or a microwave or red light or violet light or X-rays. They all travel at that same speed. However, in a different medium, glass, plastic, water, some other medium, the speed of light is different. 4 different wavelengths. Okay. In other words, if we're not in a vacuum, the speed of light depends not only on the medium of the light, but actually it also depends a little bit on the wavelength of the light. If you look in your textbook in this page number, I should verify it, but in your textbook in this chapter, you'll find a chart that shows you what the index of refraction is for different colors of light. I'm going to get a textbook and see if I can find that for you. So we're looking at page It's page 752. So if you look in your textbook on page 752 at figure 23.29, it will show you a graph of how the index of refraction varies with different colors of light. For flint glass, red light will be N equal 1.61, but violet will be N equals 1.66. What that means is when we do the math, the bending, the refracted angle is going to be different between red light and violet light. Let's look at that example. Let's make a little bit more room up here. I'm going to let this side be air. I'm going to let this side be flint glass. Remember, when we enter something that is more optically dense or has a higher index of refraction, we expect it to refract towards the normal. So it looks like the violet light is going to bend more towards the normal than the white light. So we'll let green represent white light just because. So I'm going to let my green light come in at a 30-degree angle. But I'm going to say that this is white. White light contains all of the colors of the spectrum. So I'm sending white light in. And we're going to look at how the red part of that gets refracted and how the violet part of that looks refracted. And the other colors would be somewhere in the middle. So if we look at red, well, we're starting at air, so 1.00 sine 30 degrees. That's the air side, has to equal 1.61 sine theta. I'll put R for refracted. Well, for red light, when I solve this, I get the refracted light is at 18.1 degrees. So it refracts towards the normal, and it makes an angle of 18.1. So here we go. So that is 18.1 degrees for red light. If I repeat that, only now I use 1.66 sine theta R, I find out that for violet light, it ends up at 17.5 degrees. Again, I don't have a violet marker, but I used, and that's going to be at violet 17.1 degrees. Okay. Obviously, the farther apart you get back here, the more obvious. And the other colors in the rainbow would be, remember this is red, orange, yellow, green, blue, violet. So we could see all the colors of the rainbow. That's how a prism works. It works by dispersion. It's also how a rainbow works. In fact, the water droplets in the air act like little teeny tiny prisms that cause these colors to separate. Okay. A lot of times a problem will ask me about the angle of dispersion or this difference. That angle of dispersion or that difference between the red and violet in this case is 18.1 minus 17.5. So that angular separation there is about 0.6 degrees. Again, it's pretty small, but nonetheless, we can make a rainbow out of it. So it is significant. That concludes this section. We have one more section in this chapter. It's over the idea of polarization. So I'll be doing a lecture over polarization in just about 5 minutes.